one-way blind here. So my name is Amir Hossein, and I'm a PhD student at University College Dublin, working with Dr. Philip Cardiff and Dr. Vikram Prakash. So my work or my research is mostly about developing a new numerical method called Simo Reissner beam method in order to model the mooring lines attached to a floating body. So in order to start, I would like to begin with the definition of the mooring lines. So as you see in this picture from NREL, you can see a wind farm. So there are some lines attached to each wind turbine that's usually they come with the main two reasons of using mooring lines are the first one is we should connect these platforms to the seabed. In the other word, just holding them in the position that we want in order to form the wind farm. And the second one is that we can also contribute to their stability. For example, so there are some methods that I think in the industry they use to hold them stable in the orientation that they want. So you can use the mooring lines with some workarounds to hold them stable. So mostly this stability used in the tension leg platform. So these yellow structures are called tension leg platforms. Also, you can see that we have in this picture we have two different mooring lines, two or three different mooring lines. So the first common is the taut mooring lines, which you can see it's not a stretch, it's a stretch. And the second one is the kind of which we call slack mooring line. So you see that there's a length and there's a form of the category. So what we are going to do about this is that so we have a tool developed in our research group, so which I'm going to discuss in the couple of slides later. So this tool is able to capture the nonlinearity of a beam. So it can model a beam. So based on the title that you saw, it's called the Simo Reissner beam theory. So when you can catch some nonlinearities, so you can capture the large displacement. So this tool is kind of ideal for large displacement kind of structures, which mooring line also, since it, due to its nature, kind of dealing with the extreme flow conditions, usually they have large displacements. Also, based on our understanding during the literature review, we observed that the bending and torsion, they're missing from the current studies. And to this date, there is no native open form application or native open form solver for this mooring line or mooring line simulation. So this seems to be less important as these the first one and second one. But if you think more of it as a tool which can lead to a two-way coupling, so you can see that it's also as important as the first two ones. And also by two-way coupling, I mean that the beam can also sense the surrounding fluid. So if you have this kind of FSI simulation with a kind of arbitrary beam solver, your beam can sense the surrounding fluids. So to this date, every approach that we actually encountered during our research, we found out that they have a kind of quiescent flow assumption around. So the beam is totally blind about what's happening around you. So in order to just, in a very kind of general way, classifying the different modeling approach, so we reach these three terms based on the fidelity of the model. So fidelity here is a kind of ambiguous term. So my understanding from this fidelity, because if you search for the literature of the mooring lines or any other offshore simulation kind of software or the model, you reach this fidelity. So my understanding of this fidelity was the nonlinearity. So the higher nonlinearity you can capture within your model, the higher your fidelity is. So, for example, in low fidelity models, for example, such as Flores, these names also have some kind of active GitHub repository. So if you search for these terms, you can see that there are people working on them, and there are kind of progress or development happening on these kind of code bases. So, for example, in Flores, they only just consider the wake model, and you can see that they only consider what's happening in big picture. And the other mid-fidelity approach, like FastFarm or OpenFast, based on their description, they're just some linearized model for fluid. So they don't solve for the fluid as most of us will do within OpenFOAM. So they just have a potential flow assumption within their fluid. And more recently, in high fidelity models, they have some separate mooring line model connected with the CFD-based approach. For example, this Moordyne and Moodye, which these two are two famous mooring line simulator, which Moodye is based on finite element and Moordyne is based on lumped mass approach, which I'm going to talk in the next slide. So they connect the approach that they have for mooring line with the CFD approach. So in terms of fluid and what's the forces coming from the fluid, it's kind of a high fidelity approach. In order to just review what's happening under the hood of the Moordyne, so the equation for the Moodye, which is based on finite element, is quite kind of complex, and it's hard to just summarize within one slide. But in order to just mention the lumped mass approach, which is a kind of common way to deal with the mooring lines, especially within Moordyne. So I'm just going to review what's happening. So it's a kind of easy assumption. So you can just discretize your whole mooring line into some points and to some nodes, which they have a point mass. And you can easily write the actually F equals to MA for each node that you have with some source terms. So, for example, you can have tension for each node, damping, buoyancy, and weight, and also drag. So when you solve the such system of equation for the whole beam, you can easily connect this to a CFD solver and then solve for your mooring line. One thing is also important here that, for example, in Moordyne, they use Mersenne equation for the drag. So as you might know, Mersenne equation is kind of a simplified estimation. So although it has been proven to be kind of accurate enough, but also there might be some scenarios that the Mersenne equation might not be accurate as we know. So it's what's happening in Moordyne. So if you solve the similar system of equation, you can solve the mooring line over time. We have the beam theory called geometrical exact Simo-Reissner beam. So this work has been done in our research group. So I would like to actually forward you to this paper. You can see this paper done by one of my colleagues in our research group named Shivani Bali. So they actually derive these equations from the scratch. So not from the scratch. So they worked and discretized the integral form of the equation into a cell-centered finite volume. So these equations are linear momentum and angular momentum, and followed by two constitutive relation. You can solve for any force vector based on the displacement, and also you can discretize these equations on a finite volume. And then when you can solve actually discretize it on a finite volume, you can easily code it within OpenFOAM. So we have this approach implemented in OpenFOAM called BeamFOAM, which is just a beam simulator. So the goal here is to take advantage of this BeamFOAM as 6DOF rigid body motion restraints to solve for the mooring lines. So this 6DOF rigid body motion is OpenFOAM's built-in class for kind of simulating the motion of a rigid body. So I'm not going to enter that topic, but just a quick review is that within 6U of rigid body motion, you have some restraints and some constraints. So restraints and constraints are actually the same, but if you want to delve into the word itself, and also if you look at the equation, you can see that the restraints can contribute to the motion of this rigid body. So as you see, we have two we have actually the linear and angular velocities, so that they're just Newton's actually Newton's second law. So we have an external force and external moment. So these external force and moment are happening within the restraint, not constraint. So but by constraint, you're just constraining your motion. But with restraint, you can also contribute to what's happening as a movement on that 6D of rigid body. So these F and M here are called external force and moment. So within this external force, you have a term called restraint force. So by restraint force, for example, you can calibrate it to act as a force coming from the mooring line. So here is a good way, which is, I think, the first paper that implemented Moordyne within OpenFOAM also used the same approach. So it's a good way of kind of coupling an external solver. By external, I mean external from the fluid solver to any fluid solver within OpenFOAM. So I know that might sound a little bit of a confusion here, but in order to just review what I've just said is that, for example, imagine a interfoam simulation. So you enter the pimple loop. At the first time, you have a floating body motion solver. So in which first you will calculate the fluid forces, then you will go calculate the restraint forces. These restraint forces are actually these restraint forces are these F and M, forces and moments. So these forces are coming from the beam solver in our case. Then you will reach the 6D of rigid body side. Then you will reach the 6D of rigid body motion restraint, which we kind of developed our own restraint library in which we will update the beam boundary condition. So by beam here, I mean the mooring line. What's happening here is that I'm going to, based on the previous iteration, previous value for the displacement of the rigid body. So I will just update the boundary condition of the beam and then solve for the beam and then extract the forces. And the following, we are just going to update the velocity, position, and then we will move the mesh and body and V of advection and turbulence, and that's all. So the only thing happening here is that in this restraint, I will contribute the motion of this box or the rigid body that I have in my simulation. Also, since it's an OpenFOAM workshop, I think some people might be interested in what I've just described in the previous slide, and I will describe it in a code. So I will introduce a variable called restraint position, and I will use a transform method to track the reference attachment point. So this reference attachment point is the point that I say that, for example, track this point. So I will apply my restraint at this point, and then I will calculate the attachment displacement. This W is the displacement coming from the beam solver, and I will, based on the value that I have for displacement, which I calculated, also based on the previous motion for the rigid body that I have. So then finally, I will apply this W, the value of this attachment displacement as a boundary condition for the W, and then I will solve for the force by using the evolve function that I have. So in order to just be a little bit faster, because I think I have a kind of limited time. So in order to validate our approach, we use the experimental test case conducted by Wu et al. At Ghent University. So it's a very famous when you perform a literature review for mooring any moored floating object or anything like that, you will encounter definitely to this case. So it's as you see, there's a box floating on a wave basin. So it's also the top view of this experimental setup. So the wave is coming from the right, and there's a wave absorption on the left. So there are some load cells which tells us that they capture the value of the tension or anything on the anchors on these load cells. So you see that there's a iron chain mooring line attached here, and there are some sort of actually experimental setup devices attached to this box. Also, you can see the experimental properties of the box. For example, box mass is just to give you an idea of what's the mass and what's the dimension of the box. So you can see that this is the dimension and this is the mass for the box, plus these iron chain connections. Also, based on the wave gauges attached to the on this experiment, we reached the kind of wave type which we use the built-in open-form wave generator. So here's our numerical model replicated from that experiment. So it's kind of easy to understand what's happening here. So we are propagating wave from the left similarly, and we are absorbing the wave to the right. We have 4 different mooring lines, as you can see here. Just to mention the boundary conditions, we have stationary walls on the left and right. So you just might be curious of the number of computational cells that we have in our domain is that 5.6 million, and for 16 seconds of simulation time, by using this 144 AMD, using this iCheck, is an Irish high-end computing center. So it's about 32 hours to just simulate for 16 seconds of solution. Before I enter the results and discuss about what's happening in the results section, I will just mention a few things about the simulation setup here. So the first one is that from here I will call this point which is the attachment of the mooring line to the box that I have as a fairly, and the other one is as an anchor point. I have a region here which is a seabed ground contact. So the way we implement this is that we define some based on the experimental results that we have, we define some ground coordinate, and then we apply the penalty for this ground coordinate. So the ground working as a spring damper, so they will apply penalty force. So as you can see, the formation of the beam here is like that, it's lying on the ground. The other thing is that, as I said on the previous slide, the mooring lines, the mooring line is an iron chain. So if you have an estimation, if you have a number of the Young's modulus for iron chain, it's in the order of gigapascal. But since it's so since we are not replicating the exact experiment, which I will discuss in the next slide, so we have to calibrate, the previous numerical works on different frameworks, not only OpenFOAM, also had to calibrate their own Young's modulus. For example, you see that it's a very kind of small Young's modulus, but so since there are some kind of assumptions within the model, so we had to use a smaller Young's modulus for our case. So just a quick animation of our simulation. So before I play the animation, these lines on the alpha, the volume fraction contour or the processor patch. So you can see that the wave is coming from the left. And the other point is that, as I said, the box is not constrained here. So the box is free to move within the domain, but the presence of the mooring lines actually, they kind of confine the box and won't let it get away. The good thing on this animation is that kind of we can see that everything is kind of working physical. So in terms of contact, because it's if you come around to simulate such a problem, so the ground contact is a kind of areas that make your simulation unstable. Okay, so in the last few slides, I would like to discuss the results that we get. So we compared the experimental results from the Wu paper that I just showed you with our own results. So as you can see, there is a good agreement between the results and between the experimental results. I think. So yeah, sorry about that. There's a good agreement between the experimental and numerical results of ours. There are some kind of problems when you are about to replicate such experiments. For example, as I've just said, in this area you can see a kind of offset between these two type of results, and that's because in the experimental work they kind of consider a chain, but what we have in our simulation is that we have a kind of beam, and also we have a kind of calibrated amount for diameter, but in the experimental work they have a different diameter because they have a kind of chain. And also these chains can act differently between 9 seconds and between 9 and 11, because when there is no force acting on the mooring line, they can kind of actually go back to the slack state. But in our case, the behavior is different. But anyway, I think the results are kind of acceptable, and it's also they show a good agreement with other numerical works. The second part of the results that we can get from such a simulation is the results regarding the box motion. So as you can see, with heat and surge, we see a kind of acceptable agreement with our results. The only problem here is in pitch. So if I can go back to the experimental setup that I had. So most researchers, most numerical, so there's another numerical work using SPH, so the meshless Lagrangian particle simulation. So they also simulated the same problem, and they also reported that during experiment, you can see that there is a wooden plate attached to the box in the experimental setup. So this is the plate that we don't consider in our simulation, because this plate is kind of only applicable on experimental setup. The other thing is that there are some reports on the experimental paper that during the experiment, since the wave is coming from this side, so there were some droplets splashing over this plate. So these actually the plate at first place is only you can see some sensors attached to this plate. So it's just only for capturing and recording the box movement. So when there is a kind of droplets splashing over this plate, so there will be a different results. So they also justify the difference of the pitch results by the experimental pitch results using this justification that I've just said. But anyway, about the surge and heave, we can see a good agreement, but there's a problem with the pitch. Also, some other numerical open form and also with SPH, they suggest that there's a insufficient kind of 6DF motion simulation, and the offset is due to that insufficient formulation. But that's a kind of justification, and it's a kind of black box what's happening inside the pitch. So I think that's it. So what's happening here is that we have a kind of mild wave condition, so it's not as extreme as it's supposed to be, and our solver, as I've just described, is suitable for more extreme. So the point that our solver can work and the others might break is when there's a very more extreme flow condition. So one next step for us might be validating or maybe replicating another experiment which considers way more extreme waves to just ensure that this large displacement assumption that we had in the beginning also works. So I would like to thank, before I finish, I would like to thank my funding body, the SFI and Nexus, which support my project. And also I would like to thank my supervisors, Philip and Vikram, which their output also helped me during this development. Also, I would like to thank you for your attention. Sorry, I just actually extend from time. And if there are any questions, I would like to hear, and just feel free if you have any ideas. So, or if you have any questions, way more questions, feel free to contact me via email or even in GitHub. Thank you.